So hydrate compounds. They're very similar to what we would consider just a regular ionic compound. The only difference is it's an ionic compound that attracts water molecules into its lattice structure. Now, because ionic compounds are made of cations and anions, they have charges, they have alternating patterns of those anion-cation charges. And obviously water is a polar molecule, so it has partial charges. It attracts to those particular cations and anions to a certain amount. So like different ionic compounds incorporate or attract different number of waters in there. Now you can tell how many waters are attracted into the formula unit by looking at the coefficient number in front of the water. Like right here, this coefficient number in front of the H2O. Okay, so here, as you can see, here's your copper, here's your sulfate. That's copper 2 sulfate is the ionic compound. Around it is the 5 waters. Now 4 of them form an attraction with the copper, and as you can see, the oxygen sides are facing in because that's the partial negative side. And then over here towards the sulfate, you have 1 water where the hydrogen side, which is partially positive, attracts to the negative anion of the sulfate over here. This is just kind of like the ball and stick models of the molecules and how they attract into the structure. Now we're going to go into like ball and stick models and Lewis dot structures and all of that next unit. Be a lot of drawing and things like that. But general idea here of showing how like the waters incorporate themselves and attract into the formula unit. It's always written with the ionic compound first, and then the coefficient that tells you the number of water molecules that have been attracted in to the thing. With the dot in between, of course, the dot's basically saying the copper sulfate times the 5 waters. Now, we're going to calculate the percentage of water found in the hydrate here. And this one, you see it has the iron phosphate. So this is actually iron 3 phosphate. If you remember that phosphate has a -3 charge. So if there's one of each, that means the iron over here must be a +3 because of course the charges must add up to 0. So this is actually iron 3 phosphate. Now, to name the hydrate, we use a prefix system, and we'll go over this later, but because there's a 4 in front of it, that would be tetrahydrate, saying there's 4 waters in there. Looking at here though, we want percentage of water. So I'm going to break it up into like the ionic compound section and then the water section. So we're going to have like the FePO4 up here and then the water down here. So iron, phosphorus, and oxygen, of course, this one's going to be times 4. So we need 4 of them. Down here, we have hydrogen and oxygen, and of course, this one's going to be times 2. So before we can continue, we need the periodic table to look up the molar masses. Remember, we're always rounding to 2 decimal places. I want 2 decimal places per molar mass so that we all have the same numbers. So if I'm looking here at iron, that would be 55.85. Looking over here at the phosphorus, that's 30.97. And then oxygen, of course, always rounds to 16. So it's really 4 times the 16 here. Down here for the water part, here's hydrogen, 1.01. So it's going to be the 2 times the 1.01. And then there's 1 oxygen, so that would be 16. Okay. Now we have our numbers we can move ahead with calculating. So here, of course, 55.85. Here's your 30.97. Those are just 1 each, and then this would be 64 for the 4 oxygens, and we could add those up. Now add those up and get the mass of what we would call the anhydrate, or the ionic compound portion. The ionic compound portion of the compound, which happens to be 50.97 grams per mole. Now for the waters here, I like to just calculate water, and water is a good one to memorize because this would be 2.02 plus 16. So water's molar mass is always 18.02. What you have to remember those, because there's 4 of them, then we have to multiply it by 4. So the mass represented in this compound is 18.02 times 4 because there's 4 waters. So the total mass of the water happens to be 72.08 grams per mole. Now we know, and we can figure out the entire molar mass. The entire molar mass is 50.79 plus 72.08. Did I calculate that right? Let me see. Oh, this is 8.2. I think I did that wrong. I put this in my calculator wrong. Everybody else got 8.2 there. Sometimes I punch numbers incorrectly as well. So I'm getting 222.90 grams per mole. This would be for the entire compound. Now we want the percentage of water. So we take our water amount and we divide it by the entire amount times 100 to get our percentage. 72.08 divided by 222.9, and that's going to give us 32.34% water. You might want to go ahead and check my math and make sure I calculated that right. And because like I said, I can punch numbers just as terrible as anybody else and make mistakes. This was an 8.2. Now that we have completed the water part, and usually for a hydrate they like to ask about the water, but they could ask about other elements too, like phosphorus. Well, we know how much the phosphorus is because we know that from up here. And we know the total already because we already calculated that. So this part should be pretty easy. The phosphorus over the total times 100 will give us the percentage of phosphorus in there. And obviously its mass is less, so the percentage should be less. And it is. It's like 13.89% P. Phosphorus. So the hydrate problem is the hardest for percent comp, obviously, because you also have to incorporate the water into the mass. The molar mass of the water does count as weight in the compound, but it is still the same concept of a regular percent. You're taking the part over the whole times 100. In our cases, the parts are either going to be the element or the water, and then the whole would be the mass of the entire compound times 100. And there's, of course, the correct answers.